So if we look at direct variation as multiplication or linear equation as multiplication, so we were saying that speed is equal to, distance is equal to speed times time. Then if the distance is constant, right, let's say it's 5 kilometers or 10 kilometers, distance is constant 10 kilometers. Then if you go at a speed of 1 kilometer, you will take 10 hours, right? So this is 10 kilometers. And so if I have 1 kilometer per hour, then I'll get that the time is 10 hours. So basically the time is, the faster I go, the lesser time I take, right? So if I'm going at 10 kilometers per hour, the distance is still the same, 10 kilometers. But now the time is 1 hour. So the faster I go, the less time I will take. So this is where you get, so time is basically distance divided by speed. This is a constant. So when you had a multiplication story, speed into time is distance, that can be written, converted into a division story and what happens to time. Then it becomes an indirect variation. In indirect variation, the product of these two quantities is going to be a constant, right? So as if you thought about it in terms of S versus T, right? Then as the S increases, the T will keep decreasing, right? And as the S becomes smaller and smaller, the T keeps increasing. So the curve looks like that. You have to remember that the product is constant. ST, the product is constant. So if I take a value 1, then this will be 10 and it will be symmetric. Across this it will be symmetric. Right? So if you take a value 10, then this guy will be 1. So this one was 10. So clearly the curve, since it needs to be symmetric across this, right, will, if it goes down, and we know it's going down, and it will have to go up there, right? And so the interesting thing here is, of course, that the product is constant. Now remember, product is area. So what we are saying is that this area is always going to be a constant. Any point you pick on the curve, the area is going to be constant. Now, you know, when something is very narrow, right, then it doesn't have much area. But as it keeps getting broader, right, as the width keeps getting broader and becomes more rectangular, then the height doesn't need to be so much to get the same area, right? So if I go to 2, then this is going to go down almost to half of that. It's going to go down to 5. It's not even drawn right, maybe half or somewhere here. But anyway, you get the picture, right? That basically the curve is not going to be a straight line. You may have imagined, okay, if it needs to be symmetric, I agree, it needs to be symmetric, but why like this? Why not like this or something, right? So the reason for that is that what we are talking about is that the area of that curve, every point on it, the area of that curve needs to be the same, constant, which is 10 in this case. So as we keep getting to the root of 10, where it will be a square, right? It will be a neat square somewhere. So that square will have the shortest height and the shortest width. It'll basically be this point, right, where it turns. And after that it again starts becoming longer and thinner. So there will be some point of where it is, the length and breadth is the same. And it becomes a neat square, and that will be probably this point. So that's one way to look at it, that if you have any point on the curve, the area that you get of a rectangle of that curve is constant. So when you are doing a graph sheet, you can potentially do one of these 10, 20 or whatever. So the number of squares is 10, number of squares is 20. And for each point basically see, well, how many squares will be there, and when does the number of squares reach 20, and that will be the point that will be here. So that's one way of doing it without any calculation, which might be an interesting thing. So basically with graph paper, take x values and count squares in a rectangle where you get the constant for the and that's basically I think an interesting way of looking at indirect variation.